So hello. Yeah, today we dive into a new experience. So let me first show you how I basically got there, like where I started to dive into embedded development with Erlang. It all mainly started with this device, which is a flashing device for automotive ECUs, like equipment for manufacturing or for flashing big stock or whatever. And the architecture of this one was that there was a FreeBSD industrial motherboard inside because it's a rather big box, and there were some gateways where an embedded operating system was running called RTEMS, and which basically just translated whatever was spoken on the USB by the Erlang VM. So I had a USB driver for the Erlang VM. I'm talking USB to a gateway, and the gateway basically talks the automotive protocols I needed to actually build the device. So if you look at the operating system of the gateways, it's called RTEMS, and this will stay with us. So since probably a lot of you don't know what RTEMS is yet, let me give you a short intro. So RTEMS is a hard real-time OS, but OS with quotes, because it's actually not a normal OS. It's more, the E in RTEMS means executive, so it's a real-time executive, which means that you take your application and you link it together with the operating system, and then you basically boot this on hardware, right from reset if you want, or from a bootloader. Actually, I mean, this has been done for a long time in embedded and didn't have a special name, but it recently occurred to me that there's a new name for this. It's called unikernel. So actually, it's a unikernel. I link together the application with the kernel and run it on the hardware. I mean, most unikernels don't run on real hardware, but RTEMS runs on real hardware. So what kind of hardware can it run on? It can run on pretty small RAM, but that's not important to us in this context, because the Erlang VM wouldn't fit into 32K of RAM. So it runs on very small machines, and it's very efficiently switching threads. So it doesn't have tasks. I mean, they are actually called tasks, but there are no processes. It basically looks like there's one process running everything, having several threads. Hello? So in the context switch between these threads is very fast on a very slow machine even. This is kind of historic. I probably have to go to a museum to get a machine with this CPU. There's a POSIX API in RTEMS among several others, which are more important for other embedded applications. The POSIX API is the most important for us because it actually helps a lot porting the Erlang VM to this. And so we don't have virtual memory and all kinds of other things that normal operating systems have. If there are some, you have device drivers, but device drivers are basically just a library that you link with your code, and which helps you talk to the actual device. So it's not a real device driver. So I just mentioned porting Erlang to this. The setup in the box was kind of inconvenient for other applications because, for one thing, that the Erlang is pretty far away from the hardware. So you have latency, which you have to deal with. So you have to have some smart queuing on the gateway, so to get rid of the latency, to get some flow control going on like this. And also, I did smaller embedded systems work, and I wanted to use Erlang there too. So I tried it out, and it worked actually quite well a few years ago. I ported the Erlang VM on the RTEMS kernel, which basically means that you get an executive which you can boot on the hardware. I mean, real bare metal. I mean, that's why. I mean, I have to say real bare metal because bare metal in the meantime means running on some large VM management thing, inside VM management thing, 3 layers deep, and then they call it bare metal. I don't see any metal in this, it's virtual metal. So this, I'm talking about real metal. Except that silicon is not a metal, actually. So the architecture of the whole setup, if you have the Erlang VM on the RTEMS thing, you have your Erlang code, runs on the Erlang runtime, and the Erlang runtime uses the POSIX API to actually talk to the hardware and to use, for example, the TCP/IP stack of RTEMS. We actually have a choice of 3 TCP/IP stacks from very small to the current FreeBSD TCP/IP stack with SMP support. You can add to this another application written in C. If you have some parts in C, some libraries or some other legacy stuff, you can have this on the side. And from your Erlang code, if you call a NIF or a LinkedIn driver, or also known as port driver, basically you call out from the Erlang VM to C, and this C is directly talking to the hardware. So you have very little latency between something happening on the hardware and some like a message received on the Erlang VM, which kind of makes the soft real-time stuff of the Erlang VM much less soft than it would be on a Linux kernel, because there's you know exactly when your Erlang VM will be preempted. So if you don't have any threads that have a higher priority, it will only be preempted by interrupt drivers. And you probably should know when and how often these trigger. So with this setup, there was a customer project for a company called Bosch Rexroth, subsidiary of Bosch, which you probably know. And for them, or in this project, we built smart transport controllers. So that's basically smart conveyor belts. Everything under the keyword Industry 4.0. Sometimes a little bit Internet of Things thrown in. Cyber physical systems is also a keyword, a buzzword there. But yeah, that's just buzzwords. So to show what we're actually doing with this, I want to show you a video. So this is one of these conveyors, and everything that's moving currently is controlled by a network of Erlang nodes, so 15 Erlang nodes. So you see the Erlang nodes, and they are without box, the thing with the blue cables on it. Yeah, they're not very visible. So they are strewn in between. So you have these lifts that detects their sensors. Then there's our RFID stuff on the node, which is also controlled from Erlang. And sometimes you have to fix the stuff if you want to work on it. So this is just an empty conveyor belt, a demo thing. So I always wanted to basically give this back to the community, submit my code back to OTP, but there was always the hurdle that it's kind of, I mean, Fred this morning talked about that it's kind of like a hassle to get started with Erlang. If you try to start with RTEMS on real hardware, that's a real hassle. Much worse, much worse. Learning curve very, very steep. And so I always feared that nobody would use if I would just put out the code, nobody would build something with it. And a while I thought about writing sets of drivers and ports to like Raspberry Pi and BeagleBone, but basically this also has a cost, and you need more variants of drivers, and you don't control the hardware, and people like have to put stuff together themselves. And also that the kind of embedded hardware you get usually is either too large, like a Raspberry Pi. I mean, it can run Linux, and you don't need to have Erlang running on the hardware. You could do, of course, and then have the hard real-time stuff going on, but yeah, you actually don't need a Raspberry Pi, and it doesn't have that many I/O. Also, the BeagleBones are too large, and if you go to the lower end like Arduino, those are too small. Can't run Erlang on it. Not enough memory, nothing. So that's why a while ago I decided to design a hardware especially for this use case. And a hardware that's available and that's affordable, and where I can basically combine the hardware and the driver and a software tool set, so everybody can get started very, very quickly with Erlang and some real embedded systems project, or maker project, or robotics, or Internet of Things, or whatever. So this board has arrived. It's here on the table. Unfortunately, it arrived. I got the first working board on Monday evening, so the demo has to be a little bit limited. I don't have a robot with it yet. So this is the board. Let's just rush through the different parts of the board. So that's the CPU. It's a Atmel CPU, but it's not the Arduino class CPU from Atmel, but it's an ARM core. It's a Cortex M7. That's the largest mobile, low-power ARM design that you can get. So it has 32 bits and an FPU and everything you need. Another interesting piece of the hardware, as you might have noticed, there is no Ethernet plug on the board. And kind of if you run Erlang, you kind of want to have a network. And so since Ethernet is kind of old school, we put Wi-Fi on by default. One can connect an Ethernet adapter if one is old school. But yeah, if you want to run Wi-Fi, you can run Erlang distribution over Wi-Fi. So we need something to boot from, and this is this little slot, and it boots these little, no, I don't have one lying around, micro SD cards, which you also could put in Android phones, but not in iPhones. When we boot, we need to load we load stuff into some memory. There is some memory on the CPU because it's actually an embedded automotive CPU, this kind of CPU. It's actually for multimedia applications in the car. And so the onboard, the on-chip memory is only 300K, 384. So that's a little bit small for running a normal Erlang. And so we added a little bit more memory, and since the CPU supports SD-RAM interface, we added one SD-RAM. 64 meg is plenty for Erlang in this setup. Really plenty. I have the same amount of memory in the other device that you saw the video with, and I never checked like how much memory my stuff uses because I'm so far from the limit that could put a little database in or whatever. You have to connect to the board and have to debug it somehow. So there's a USB connector to it, and it gets powered by the USB connector, so you can power it by your laptop. But you can also use a normal USB power supply, of course, or a battery, USB battery. So you can get all kinds of sizes of batteries, but you have to load them extra. So you have one of those USB batteries, you charge them, you connect them, and it runs. So it doesn't have a charging electronics on or something. So this is the user interface, the input. You have five little switches, which you can set to on and off. The sixth one is taken over for changing the debug thing. Oh, I forgot to say, on the USB interface, there's also the serial console, and there's also an onboard JTAG debugger. So you can do hardware level debugging with a very cheap adapter to access the onboard JTAG debugger. And then you can basically single step in the hardware. There's also a JTAG connector in the corner, which I didn't highlight, which is for one of the big JTAG debuggers, which have more features, but are much more expensive. But I found it important that there is a cheap hardware debugging facility accessible to everybody. So the other part of the UI are these two little white dots. That's our two RGB LEDs. So that's the output. That's a little bit limiting. So we added a lot of connectors. So the row of black connectors on the board, on the border, they're actually PMOD connectors, which is a standard by Digiland, and where you can get about, last time I counted, it was like 80 plus different sensors and actuator boards, which you can just plug into these connectors. There are different kinds of these connectors. So the first one is a GPIO. So I will talk a little bit more about the different interfaces to explain what they are. The second one is also a GPIO because you need usually more than one. And the third one is a UART, which is basically not normal serial console thing. But in this case, it's not the 12 volt plus minus, which is the normal serial cable, which were on very old PCs. But it's basically 3.3 volts. So, but there is some hardware which you can directly connect to a UART interface, and then you actually want to have one of those plugs. The next one is SPI. SPI is an interface which is almost as simple as GPIO, but gives you more options because it's serial, and you basically shift bits out with the clock, and then you can, lots of chips directly can support SPI. So then, since there are a lot of chips that support SPI, there's a second SPI. This one is a little bit higher. It's an extended SPI. It has two interrupt lines as input. So basically, your chip can basically interrupt back and say, I have some data for you, and then you fetch it with a synchronous serial thing. So actually I left one interface. So this tiny connector, the 3 pins you see, that's a Dallas 1-wire interface, which is also a low-level interface, but has different characteristics. I'll explain later what it does. Actually I left one off. There's one connector. Oops. There's one connector just beside the keys. That's actually I2C. It's on the top. It's on the top because usually you have a cable going from, you can connect several boards to the one connector, and you have a cable hopping from one to the next. So that's why it's on the top. So that's the hardware. Oh, it wants to go through this. Oh, sorry about that. Let's stop this and rush on to the next slide. Okay. So there's basically the data I already mentioned of the CPU. It basically has all that you want. It's a 32-bit CPU, ARM Cortex-M7. It has DSP extensions. But for DSP extensions, we actually need to put a driver into the thing that kind of NIF driver that you can actually use them. But finally, eventually, I plan to basically make almost everything available that is on a chip and accessible from Erlang. You have a FPU, and so the memory, as I mentioned, there's an internal flash which only is used for the bootloader. So the little program, which incidentally is also RTEMS. So RTEMS is the bootloader and is used for running the Erlang VM at the same time. Because it's so small that you can build a very small bootloader with it. Actually, you don't need most of these 2 megabytes. And the SRAM I mentioned and the other RAM. There's also an EEPROM where you can like store configuration data or stuff like this. So a little bit more explanations about the I/O stuff, since we are in a software conference and not in a hardware conference. So GPIO, a general purpose I/O, which is called, it's just basically 4 digital lines which you can switch on and off, and they are mapped to bits in a register. And so these bits in the register we will make accessible by some Erlang calls, which you can switch on and off the bits or set them all at once, or also have some driver support to do some pulse width modulation, so have like basically a rectangular wave on the thing where you basically can send a value to the driver, and it then makes the wave, the on time longer or shorter, which you can, for example, use for the LEDs, which are also connected to a kind of GPIO. So every LED has 3 IOs. One for every color, And if you do pulse width modulation, you can get all the colors that there are. If you only switch on and off, you only have 8 colors. And none. I mean 7 colors and none. Or off. There's also a reset button because it's kind of convenient if you can just reset your thing if you crashed it. So SPI and I2C are kind of like variants on the same theme. There are serial interfaces, which has the advantage that you save a lot of like I/O lines. So with GPIO, if you have lots of things going on, you need lots of pins on the CPU, and they are limited. I mean, you can do more useful things with the pins, and you need less wires. So if you have a serial protocol, then you need less wires. And in case of SPI, usually you have 4 wires. So there's basically it's a so-called master-slave protocol, which very recently has become non-political correct. But since it's basically encoded in the I/O lines, so the MISO and MOSI means master in, slave out, and master in slave out, and master out, slave in. So these are the 2 directions, so it's bidirectional. So that's where the data goes, on and off. And then, so you know how the timing is, there's also a clock. And you need to configure, because every chip can have different things on which time of the clock you basically change the data, and on which it reads the data. So there's 4 combinations there. Basically, inverted clock or normal clock, and rising edge and falling edge, basically. And what one needs to do is basically look up what the actual chip wants, and set one of the 4 things, and then off you go. There's also a 4th line, it's the chip select, which basically tells the chip that now comes some data. It's for you. So this makes it possible to actually share SPIs with several chips if you want to. So for example, if you have lots of SPI interfaces, you could add the GPIO and use the additional I/O lines as chip selects, and then drive this manually and basically say this chip, and then you send the data, and then that chip, and then send the data, etc. So I2C basically makes it more easy to address more than one chip, because it's a bus. So you have a bus. You have basically only 2 lines, a data line and a clock line, and ground and power. Yeah, I mean, you always have ground. And it's also a master-slave protocol, and the slaves or clients have a built-in address. Sometimes it's fixed. Sometimes you can toggle a little switch on the board and say, yeah, have some alternative address. And then you can basically, if you know the address, you basically send out 1 byte the address. I think that's, yeah, it's 1 byte address. You send out 1 byte address, and then you send a data packet, and then the chip answers with the answer to the data packet. So you have a little bit more high-level protocol, but only by so much. But then you can talk to many chips, but this is used normally for talk on the same board, not like talk over with the sensor over there. Some people use it like this, but that's actually abusing it, and it's not very. It doesn't work too well if there's some noise in there or something going on. So there's a kind of extension to I2C. It's called Dallas One Wire. It's called Dallas because it was invented by a company called Dallas Semiconductors, and it does everything on 1 wire. Well, it's actually a lie. You need a ground wire, but you actually only need a ground and 1 other wire. And over the 1 other wire, you can power your opponent, so you can send power and data, which is kind of cool. So you basically have 2 wire, very thin wire, and you can just power a temperature sensor and read it out. And so it's quite similar to I2C. It's an extension of this, but it's much slower and has a little bit more data protection. There's a checksum. And what's also a neat feature is that every device, I mean, with device, I mean very small things, very small sensors, has actually a built-in 64-bit unique ID, which is worldwide unique. And there's a discovery protocol which gets you to find out what IDs are on the bus. And then you can have many sensors on one bus, and you actually know who is who. At least once you had configured them. I mean, still have to know if ID 123 is the sensor over there, and 456 is the sensor over there, of course. But yeah, that's very good, and it also goes over long distances. So I was talking about like sensor here, sensor there. So you can basically wire several sensors in a house or on an experiment and talk to all of them over just these 2 wires. Actually, the 2-wire thing has also a 3-wire pin, so further lies. There's one more wire because you can have additional power if you want to. But it's actually capable of powering out of the data line. So there's a little capacitor in the devices, which basically keeps it running over the gaps when the data is low, which is kind of a neat feature. So there are several form factors where you can get these sensors or devices. There's a traditional form factor TO92. That's basically the form factor that the normal plastic transistor had, like 20 years ago. That's kind of convenient if you want to have a temperature sensor on, let's say, if you want to control your heating system or your solar warm water system. That's one of the sensor form factors which are kind of convenient. You usually put them in a little pipe and glue it off full with silicon and then use this. There's also the I button, which is basically a 1-wire device in a metal button, which is very robust and which is used and basically it's like a battery, like a clock battery or something. So you have the 2 contacts on the box outside in the middle, and they're actually contacts for the opposite side. Or it has a standard form factor, and it's used for access control stuff. So was their kind of prior RFID, but it's also kind of like still used. I think the Turkish public transport system uses one of the buttons, and you have a key fob and you can just put it in. And you also get chips which have memory and some cryptographic primitives, which are the only way to access memory. So you can actually have some access control applications or other security stuff that you want to do. And then there are lots of temperature and climate sensors and whatever. There's a plethora. Mainly it's used for temperature sensors. So I've talked about the PMODs. So let's look at a few examples. So there are, of course, lots more. But I wanted to show you a few examples, which by the way, so that's a PMOD. That's the size of a PMOD. So let's look through a few. So that's, I can't see this. It's very small. This is, I really can't see. That's a compass. So a magnetic compass. And the next one is easier to detect. It's a 2 ampere motor driver. So you can connect external power supply for the motor, and then you can switch it on and off and drive to and fro. It's a bridge driver. The next thing is also for motors. It has connectors for 4 standard RC servos, which are used in model planes and stuff like this. So you can just get one of those and plug them in, or 4 of those, and then basically you have some pulse width thing going on. It's for GPIO. That's one of the reasons you need these pulse width things, because this actually controls where the sensor moves to, the servo moves to, so you can control the angle where the thing goes to. It's very easy to use, and you can do lots of fun stuff with those. The next one is a little bit larger one. It's actually also one that actually has. So everything is plugged in where it actually needs to be plugged in. So I try to get also samples of every PMOD for testing, that we can test all the interfaces. So this is a GPS with everything, all the features. I don't know all the features, but lots of features. And the next one, I think I can't read it here. It's a 3-axis accelerometer. And the last one is a 3-axis gyro. So with those two, you can basically stabilize your drone if you put the board on it. So yeah, that's the overview. A little bit about these PMODs, these little things. It's a very easy way to get sensors and actuators, and it's also a good way for us to provide drivers for common sensors and actuators, because if you would have like all kinds of sensor chips, you have like hundreds of drivers. But there is only one accelerometer. Why did I pick this one if it's so hard to pronounce? There's actually one gyroscope in the PMOD system, and we can provide a gyroscope high-level driver, and you can just get your readings then on the Erlang level. So there's also there will be also low-level drivers, basically getting I2C, SPI, GPIO, and all the low-level protocols on the Erlang level, because actually I don't want to write the high-level drivers in C. There's no use. So you can have a very minimal driver in C, and you could do anything in Erlang, because it works actually quite fine. So the demo, as I said, is a little bit limiting. So I have to move this over here. So the first working board arrived on Monday, and let's power on this. Hello? Oh, it's shrunk again. So I plug this in the USB. It's connected to the board, and you see something's going on with the lights. So something happens, and what's actually happening is that it doesn't work. Oh no, that was the second demo. Let me change the demos. Let me read on the SD card. Yeah, that's it. Actually, that's supposed to happen. But actually, I wanted to show you this one first. So these are the SD cards. Easy to lose and hard to write on. So that's the second one. I just put it in and push reset. And then you see something's going on with the thing, and then this LED changes color. So this is not much to see, but what happened actually is that the bootloader booted the hardware. It actually read a little program that's not in Erlang yet, but it's in C, from the SD card. And the little program actually changes the bits on the 3 lines of the RGB LED. So in order to see a little bit more, let's look at the serial terminal. So yeah, it works. So I reset it again so you can see the boot process. So that was all. It's booted. So 2 seconds. I do it again. Done. And actually, currently, the SD card driver is polled, and the CPU is running on a slower speed, and nothing's optimized. Of course, to boot an Erlang, the Erlang VM, basically to boot the image would take a little bit longer, let's say 3 seconds, then it should be booted. Maybe we can optimize it to like 1.5 seconds. And then currently you have the so-called RTEMS shell, which is a very minimal way to interact with RTEMS and to debug it. But if there's an Erlang VM on the SD card, you will actually get the Erlang shell here at this prompt. And then you can configure everything from the Erlang shell. You can configure your Wi-Fi, and then you can connect via distribution with the Wi-Fi module. So the driver for the Wi-Fi is not done yet. As I said, the hardware arrived Monday evening, and unfortunately they were delayed because this conference I actually wanted to show a little bit more. And I actually tried to get the Erlang VM running, but it doesn't compile yet completely. But there hopefully will be a demo tomorrow in Claudia's talk, where we actually have the hardware of the industrial thing which does the same thing, where you can see that it actually runs. So let me show you that actually something is done on the SD card. So let me take out the SD card and push reset again, so it does flash with thing. Now it's red blinking, no SD card. That's actually a bootloader error. And then let's put in a different SD card. That's a different demo. And boot it. So there we have actually, this is a demo which also has a SD card driver in the application. So I should be able to look at the SD card contents from the RTEMS shell. So let's see, I have an LS. So there's device and ATC is in the RAM disk, and media is kind of where it mounts stuff. So let's go to media. It's a very limited shell, so you can't do autocomplete and anything. So that's the SD card driver thing, mmcSD-0-0. And if I ls here, you can see an ini file where you configure it, and the .bin file is the actual image that gets booted. That would be your Erlang VM. And then beside your Erlang VM, you just put a release later. And then it boots the release. And the other files are some crap my Mac put on it when I mounted it. They tend to leave traces in the Macs. Okay, so let's connect it back. Yep. So about the build process. Actually, I love the topic of Fred's talk this morning, because actually was what he says we are supposed to actually do for Erlang altogether. We had in plan for embedded development with Erlang. So have a really easy build process, really easy way to start. If the board comes out of the box, on the SD card there is already an Erlang image and a normal OTP where you can actually play with the shell, and on the shell play with the hardware drivers. But we will also basically write rebar plugins, and there will be templates for new projects, for different kinds of projects, so you can basically get up and running. I mean, we've got a target set this morning by Fred, so I see this as a goal to go, but I think we can go pretty close to this. I mean, we have a little bit more complications because if we only build an Erlang release, then it's actually kind of easy because you just build a normal release with the cross-build Erlang, and you have the binary of the cross-build Erlang is just copied into release, and the rest is just normal Veeam files. So you don't have to do anything special. So as long as you only add Erlang code, it's very, very easy to build, like everything else. You just build a release and copy it on the SD card. But if you have C drivers, or need some different C drivers that are not included in the system, or building C drivers or other C applications, then you actually need to link this together with the Erlang VM, which is actually built with the OTP build process. So my plan is for this to have basically a rebar plugin that takes the OTP source, copies in the NIFs and the port drivers that you want to link, so you can configure it in the rebar config, and then it sets up some tables, and then it boots. It statically links everything. By the way, kudos to the OTP team to add statically linked NIFs. They are very convenient. Because we don't have a dynamic loader, we can't load anything dynamically. So yeah, so there will be plugins for all this stuff, and so if this is too complicated to use, you can complain to me. I promise today to make it very nice and easy to start with. So a little bit word about Erlang distribution. So the Erlang distribution can be used over Wi-Fi. There's a longer-term project ongoing to actually improve Erlang distribution, to be able on, Ericsson is also working on this, to make it able to run on more nodes, to have more like 1,000 nodes, and also to have a more easy way to add encryption to the Erlang distribution, which might be interesting if you run it over wireless. I mean, if you only run it in your own Wi-Fi, you're fine, of course. There's an older thing which was done for the initial project. EPMD can't run in RTEMS unchanged, so I rewrote it in pure Erlang, and I'm happy to announce that this has been adopted by by the OTP team to be in the Erlang GitHub top-level thing. And so this can be used as a stepping stone for actually build an improved distribution, because if you have like several ways of doing distribution, you need some addition to ePMD to actually find out what kind of protocol does this node want to talk to, or what additional protocol can we use, or whatever. And this pure Erlang ePMD is run in the same node, which I can do on the embedded node, because I know there is only one Erlang node running, because there can't be two. So I can actually run ePMD inside my one Erlang node. But you can start these source code ePMD in a separate non-distributed Erlang node and use it as a replacement for the normal ePMD for to play with. The thing is, we have the initial thing was there are more languages on the Beam, and of course, since it's just a Beam VM, you can run anything on it. We might not be able to support all of the languages in some kind of build tools, because it's probably beyond our capacity. But if anybody wants to volunteer, makes Elixir run or whatever language on the Beam, Lua, Erl, or LFE or whatever, we will help you as far as we can, and we will appreciate if you do. Yeah, there's the image attribution, and there's actually a new website set up where you can actually enter your email address and get like very occasional updates about when you can pre-order the boards and stuff like this. Oh, I'm talking about pre-order. So the price target, I can't say anything about the real price, but it will be around €100. So this is not a project to make money with it. So we will never get out the development cost, of course. So this is at cost. And it depends on how many orders we get. The more orders, the cheaper the board gets. That's easy, and there's an easy arithmetic going on there. So we have to like ramp up a little bit. So it might be that if many pre-orders are there, that actually we drop the price even before we ship the first board. Because I want to make this accessible. It should be an easy start for students. We are very glad to work together with teachers who want to build some robots with their students or whatever. So if you teach and want to use this, or if you're a student and have a nice student project for semester project, we probably will just send you a board if you describe the project to us. Questions?
Yeah.
What's the power consumption of the board, and does it have a low power mode for better applications?
So the CPU has very good low power supply as of support. So there are several modes where you can like set it to sleep in stages. The overall board, with this it depends what PMODs you connect to it. Because if your PMODs use a lot of power, then your whole board won't run long on battery, maybe. So it's not that the whole board is like a special low power battery board. We might be building something like this later, but then probably with an included battery already. But currently, so it can be run low power, and we will make use of the low power modes of the CPU. So if nothing is running, it sleeps very deeply and doesn't consume anything and waits just for the next event to happen. How long?
How many milliamperes will it?
I have no clue.
No clue.
No, I got the hardware and I didn't measure even.
Okay, can you shut down the DRAM?
Probably yes. I have to ask my hardware people. So send me an email. I will get an answer about this. So we will do measurements about the current consumption, everything. But currently, I just try to get the Erlang running. But yeah, the build process is not complete yet. And we didn't do any measurements because the hardware people, because they were delayed, they didn't do any measurements either. So it is possible to run a battery. Of course, you can have large batteries nowadays, rather large. But then they're heavy, so if you want to fly, then it's not so good. But so as soon as we have numbers, we will publish it on the website or on the newsletter. get on these nice newsletter. And if you get on the newsletter, you can win 10 boards. I mean, 1 of 10, not 10 at the same time. Unless you're the only one on the newsletter, but then you will get all 10.
Any other question?
What's the story around fault tolerance? What happens when Beam crashes or stalls out?
Does Beam crash? Actually, on these embedded CPUs, I have to get away from the antenna. On these embedded CPUs, you have a hardware watchdog timer, which is very easily integratable into the Erlang heartbeat system, which we already started to do for the other things. So you basically get then several layers of fault tolerance. You get so a hardware watchdog timer is basically a piece of very, very simple hardware in the chip, which you actually have to write several different values usually. So there's like it can't be done by accident in sequence to a register, and you can configure it how often you have to do this. And if you fail to do this, it does a hard reset on the board. And if we wire this to some heartbeat mechanism, which basically shows if Beam is alive still, then if Beam crashes, probably because one of your NIF drivers, which is the issue, of course, if you have a C driver, then of course your Beam can crash easily. And in the beginning, it probably will do often. So then you can use the hardware watchdog to even keep running, and then have the fault tolerance of Erlang on top of this. So fault tolerance on different hardware scenarios and embedded systems is a big topic which I'm doing professionally. And everything that spins off of this will be put on there too.
Okay. Yeah. Any other questions? I think we've got time for one.
You decided, I guess, not to put CAN bus on there?
Actually, the chip has a CAN bus, but the hardware dev something mumbled about that the lines are taken by something else. So usually you have all kinds of stuff on these CPUs, but the I/O lines, the actual I/O lines on the CPU are used several times, and you can't have all. So currently there's no CAN bus, but I think there's a PMOD with CAN bus. And if there's a use case for CAN bus, then just nag at me, then we might have a CAN bus on the next version.
Is it possible to cluster these boards?
Cluster with Erlang distribution or? Yeah, sure. Wirelessly. Yeah, I mean, that's the whole point. Have Erlang distribution on the Wi-Fi. And then put them wherever you want and they all talk together.
Sorry,
one more?
we're taking another one.
Okay.
Yeah, so sorry for my question. Does it, I'm sure it does, but just a question. Does it support Erlang code hot swap, like your VM you compile for?
Yeah, sure. I mean, it does everything the normal Erlang VM supports.
Like, yeah, flawless
you can have rollups, everything. That's, I mean, it's just what... the Erlang VM is actually not much different from the normal Erlang VM. Actually, not at all. It's a normal, it will be a normal non-SMP threaded Erlang VM. But actually RTEMS supports SMP, and we are actually looking at porting the Erlang VM on SMP RTEMS, some actual SMP cores, because this is a combination which actually is also very neat for lots of high performance applications. You can get lots of cores in embedded controllers, like 24 cores and a few like 16 gigabit lines on just on chip.
Great, thank you.
All right, thank you, Per. Great talk, and then round of applause for Per.
Thank you.
All right.